we have already seen that carboxylic acid derivatives undergo nucleophilic acyl substitution reactions. The nucleophilic acyl substitution reaction begins with an initial addition step or an initial nucleophilic addition step, but that's followed by elimination or departure of the leaving group or the potential leaving group. The reaction overall is substitution. The reaction overall is a nucleophilic attack on the acyl unit of the carbonyl group, and that's why it is described as nucleophilic acyl substitution reaction. Let's draw a general scheme for that reaction again. So this is the general structure for carboxylic acid derivatives, and L is a leaving group or a potential leaving group. If a nucleophile with a lone pair approaches, in general, a carboxylic acid derivative, the nucleophile attacks that carbon, obviously because that carbon is electrophilic, and it is electrophilic due to inductive effect and resonance, as we have established before. The carbonyl group is therefore broken. This is a nucleophilic addition step or an addition step which is not really different at all from that of aldehydes and ketones, but the reaction takes obviously a different course. So the intermediate then would be this alkoxide intermediate, and this alkoxide and intermediate undergoes reformation of the carbonyl group with departure of the leaving group. So the carbonyl group reforms, Cl bond is broken. That's because L is a leaving group or a potential leaving group. So the product finally is another or a new carbonyl compound. So that's L, that's a new carbonyl compound. This step is actually nucleophilic addition. This step is elimination. So the reaction overall is a nucleophilic acyl substitution reaction. That's because L is a leaving group, Lg if you like, a leaving group or a potential leaving group. This is an important class of the reactions of carboxylic acid derivative. Now, speaking of this reaction, it's worth mentioning the difference again and reiterate the difference between nucleophilic acyl substitution reactions on one hand and the traditional nucleophilic addition reaction of aldehydes and ketones. Let's draw a general structure for ketones. Okay, this is the general structure for ketones. When a nucleophile approaches ketones, it can do nucleophilic addition. This is a nucleophile, for example. And the nucleophile then, with a lone pair, obviously, attacks this carbon. And again, that carbon is electrophilic due to the same electronic reasons, inductive effect and resonance. So this is nucleophilic addition step, and if you compare the two steps, they are actually very similar. The intermediate that's obtained now is this alkoxide intermediate. This alkoxide intermediate. Now, this intermediate is similar to that, but the significant difference, as we have said and stressed before, is that this alkoxide intermediate, in the case of carboxylic acid derivatives, it has a leaving group or a potential leaving group. Now, R is not a leaving group. If it leaves, it forms a carbanion, and of course, carbanions are not leaving groups at all. They are terrible leaving groups because they are strong bases. They are unstable ions. They come from extremely weak acids, which are basically alkanes, and of course alkanes have pKa of generally 60, something like from 50 to 60 in general. So R minus or a carbanion is a very strong base, an extremely unstable ion. Therefore, it's an extremely poor leaving group. Now this alkoxide intermediate then would not expel R because of that, but rather it would get protonated. So if this alkoxide intermediate is treated with H3O plus, that alkoxide intermediate gets protonated to form a final alcohol product as a result of this protonation. So this is nucleophilic addition. So aldehydes and ketones undergo nucleophilic addition followed by protonation. So here the alkoxide intermediate undergoes protonation to form that final nucleophilic addition product, which contains also an alcohol. Aldehydes behave similarly. It's only instead of R now we have H, but again H minus is a terrible leaving group. That's because it's a very strong base. It's an unstable ion. So R minus theoretically, if we write R minus here, of course it's a strong base. It's a strong base. It's an unstable ion. Therefore, it's an extremely poor leaving group. So this is a very poor leaving group. To judge the leaving group ability, you can judge the basicity, obviously, the stability of the ion, or you can also look at the pKa of the original acid or the conjugate acid, of course. Yeah. So R minus obviously would come from RH, which is alkanes, and alkanes are extremely weak acids. The pK of alkanes, okay, is about 60 in general. You can say from 50 to 60, but that's enough to say that alkanes are extremely weak acids. And of course, weak acids produce very strong, or extremely weak acids produce extremely strong bases, and of course unstable ions, and therefore terrible or extremely poor leaving groups. So that's exactly why ketones, for example, do not undergo nucleophilic acyl substitutions, because they lack a leaving group or a potential leaving group. Aldehydes are very, very similar. Aldehydes have H minus, the hydride ion. If you want to judge its leaving group ability, H minus, or the hydride ion, is a very strong base. It's an unstable ion, and therefore it's an extremely poor leaving groups. The conclusion or the summary of this now is that carboxylic acid derivatives undergo nucleophilic acyl substitutions. The nucleophilic acyl substitution reaction begins with an addition step or a nucleophilic addition step, followed by elimination of the leaving group, and that's only because they have a leaving group or a potential leaving group. Aldehydes and ketones, on the other hand, undergo only nucleophilic addition reaction. The alkoxide intermediate, which is obtained as a result of the nucleophilic addition step, is followed by protonation. And that's really where the difference lies between the two classes of carbonyl compounds.